Acho que agora já está.
Now, yeah. We are streaming now. Ok. Bom, boa tarde, pessoal. Então, hoje a gente vai ter mais um seminário. Na verdade, o último seminário do semestre, para fechar aí o semestre. Nós temos o Prosper Nyassor, que ele fez um mestrado aqui na UFCG, foi orientado pelo professor Ricardo da Costa, e atualmente ele faz doutorado em Geofísica Espacial lá no INPE. Tá? Thank you very much, Prosper. So we may start now.
Okay. Thank you all very much for giving me this great opportunity to share with you what I've been doing so far since I left UFCG. I really appreciate the opportunity. Okay, my talk this afternoon is going to be on atmospheric concentric gravity waves over Brazil. And the outline of my presentation, actually, I'll talk briefly about what concentric gravity waves are. Then I'll go straight to the theory, which I'll not talk much about it though. And then also the methodology. Then from there, I will share with you some results that we have observed at the moment. And then I'll draw some brief summary and then conclusion on that. Okay. Just a minute. Okay, a brief question. If we ask what are concentric waves, what actually are they? This is just a simple video trying to show what they are. They are simply waves that you can see on the horizontal plane that are propagating radially outward when, for instance, you have a stone dropped in a pond where we have a still surface. When you drop a stone, you could see the rings propagating like this, right from the point where the stone is dropped, and then you propagate away from that point until everything vanishes. So that is just the basic concept of concentric waves. Now, when we talk about concentric waves in the atmosphere, this is just a schematic diagram to briefly describe what it is. In the real atmosphere, we have a layer that is between the tropopause, that is troposphere, and then the mesosphere. Sorry, stratosphere rather. So between the tropopause and then the stratosphere, we have a layer which behaves like a still surface of water. The temperature there is normally very cold, and then as a result, it makes this layer quite stable. So during the day, when you have the heating of the sun on the Earth's surface, and we have the formation of clouds, as we can see here, when the cloud gets to a mature state, what happens usually is that within the cloud, we have a layer where we have a warm air moving upward. So when the cloud moves and gets to this stable layer, it's not able to go further from this altitude or the tropopause. So it will start spreading over there. So when we have this warm air rising within the cloud, having enough energy and then vertical velocity, which technically is known as the updraft, it is able to overshoot or pushes the tropopause into the stratosphere. So if this pushing is having, should I say, enough energy to lift it to about 1 to 3 kilometers into the stratosphere, and at the same time having the behavior of a stone, when the stone is dropped into the pond, we are going to have our concentric wave generated. And then in this case, at the very altitude right above the tropopause, or the place where it overshot, we could see that the radius of this wave will become small. And as it's propagating up into the mesosphere or up into the upper atmosphere, these rings will begin spreading horizontally. So this is what basically we have happening in the Earth atmosphere, as we will observe this concentric wave now in the OH emission layer, which is about, let me say, 87 kilometers up. So when you look at it right from the horizontal plane, this is how it's going to appear, just like the way we saw it on the surface of the water. So in the Earth atmosphere, one natural way for us to have this concentric gravity wave is as a result of thunderstorm. We have other sources such as volcanic eruption, and then we have earthquake as well. But in Brazil, I would say so far, the only mechanism that could generate the concentric rings that we are observing so far is the thunderstorm. Okay, it's just a minute for this. Okay. This is just an example of a concentric gravity wave that we observed on the 1st of October 2017 in São Martinho da Serra. Now, in this image, what we can see here basically is that we have this arc-like structures propagating outward. It's still concentric gravity wave in the sense that due to the field of view of the imager, we could not capture the entire structure, just as I showed in the previous figure in the ideal case. So as a result of that, we could only observe, let me say, about 25%, that is 90 degrees of this particular concentric rings propagating away from the point where it was generated. And then over this image, you could see some black structures here. These structures are actually the cloud, and this is the problem we have with concentric gravity that are generated by convective system or clouds. They sometimes tend to cover the field of view of the imager. And then this is a light, I mean, maybe a nearby station or from the city, which is reflecting at this particular position. Then these white lines here are actually the state borders of Rio Grande do Sul. This is also a second case, as we can see here. This one appears quite, should I say, almost a complete circle. But the problem with this one also is that we really do not have, please, just a minute, let me see if I can get it to become full screen. I don't know what is happening here. Okay, still not working, but let's just forget about it. Yeah, so as we can see here, I'll show a figure that clearly shows this particular wave. So from here, we can see some structures over here propagating to the eastern part of this figure, where we can see some little dark and then bright bands appearing on the screen. So this is also another example of concentric gravity waves, which in this case, we are fortunate to have almost a complete 360 degrees circular shape. But as we go on, I would explain a little bit more about this case. And then actually it was observed on the 24th of March, 2018. Okay, to the next slide. All right, let's briefly talk about some properties of these concentric gravity waves. One of them is that they do exist in a stratified atmosphere, meaning they exist in an atmosphere with density varying with height, and then they propagate, having periods of several minutes to several hours. and then they propagate horizontally and then vertically as well as shown in figure 1. And then they have high probability of observation, having, for the concentric gravity wave, having 360 complete circular rings. If the wind in the atmosphere is little or is actually zero, ideally, it's possible we can have a complete circle without any distortion. And then to observe this concentric gravity wave, we can observe them using an all-sky imager, that is the airglow emission, and then a temperature, which mostly they do have some images that could as well do that, and then also satellite. But in our case, we adapted the satellite approach as well, which I think will be a topic for another time. Okay, I spoke about a warm region, or a region in which we have this warm air rising from the ground, forming clouds and then overshooting the tropopause. This figure here is briefly to just explain the whole concept about this particular configuration I was talking about, or description. So what happened here is, during the day, we have the cloud forming right from the Earth's surface when the sun's energy hits the Earth's surface. So we have this formation of cloud, but in an ideal case, we just adapted a cylindrical kind of configuration that this cloud will move within this particular region. And then when it gets to a region known as the level of neutral buoyancy, where it cannot go further because we have the tropopause, that very thick layer, which will not permit it to rise further, then it will start spreading horizontally, as we can see here. But then within the cloud, we have this warm air as well rising. So as a result of it rising, if it has enough energy, it's capable of hitting the tropopause and then causing this dome-like kind of shape, which is called the overshooting. Now, when we talk about overshooting, physically, if you want to see overshooting, this is how it appears in a cloud. If you are fortunate to have a cloud top visible range or observation, this is how it appears here, which actually looks like a boiling water, a point where the water boils from right from the down of this, the cooking pot or whatever material you are using. Whilst it's boiling, this is how it appears. So this is what we call the overshooting. And then we could see that we have some spreading over here, which is showing that the clouds have encountered the tropopause and it cannot go further. Just the region that is actually having enough energy that could overshoot to cause the generation of the concentric gravity wave, possibly, which has a lot of determining factors whilst it's propagating. Okay, an example of concentric gravity wave so far in literature, I'll give two examples. The first example is by Vardas et al. 2009b, where they observed this in the United States around Fort Collins, Colorado, on the 11th of May 2004, around 1 o'clock or 1:30 UT, they observed this overshooting at the top using the GOES satellite visible range. So they observed this protrusion around this region. And then in 2.5 hours time, that is around 4 o'clock UT, they observed this concentric gravity wave in the OH emission layer captured by an all-sky imager. Further investigation on the source of this wave, they realized that first point of call is that the center of these concentric rings correspond to the region where we have this particular protrusion. In this case, they use the retracing model to trace the wave from the observation altitude down to where it has been generated. So when they got to the tropopause, they realized that they have the wave path closer to this particular region, where they suggested that this wave was possibly generated by this particular protrusion that was observed 2.5 hours earlier. Another way to actually observe an overshooting is using the infrared images of satellite satellite images. So how do we know that we actually do have overshooting if we are using the infrared? One way, or the most useful way, is the temperature of the cloud top. The reason being that when you have an overshooting, the tropopause is considered to be the coldest region in the lower atmosphere. So once there is an overshooting into the stratosphere, and then the stratosphere temperature seems to start increasing, if you have this overshooting in the stratosphere, or the tropopause into the stratosphere, the tropopause temperature will look colder than the stratosphere temperature. So it will give you a distinction between what is happening from the surrounding. So once we observe this particular coldest region on top of the cloud, just as this region, which is not so visible, but it's around 170 Kelvin, the pink region over here, this signifies overshooting, which I'll show in my the succeeding slides. So for them, around 20 UT on the night of 13 to 14 May 2013, they observed this overshooting. And then after about 1.5 hours later, that was when they actually observed the concentric gravity waves over here. Oh, okay, for this, they use the VIRS satellite, which is known to be the visible infrared imaging radiometer suite. And then for this particular instrument, they have another band known as the day and night band, which is capable of capturing airglow layers in the OH emission layer that is around 87 kilometers. So for the concentric ring they observed this night, they determine the center, which is the red cross here. And then after they trace back to the lower atmosphere, that is the troposphere, they realize that the center, which is shown by the red cross here, is closer to the coldest cloud top image in the infrared image over here. So this is also an indication that there has been an overshooting 1.5 hours earlier, which is responsible, possibly responsible for the generation of the concentric gravity to be observed in the OH emission layer. Okay, so these are the only two examples that I could cite, because mostly to get the visible range for you to be able to use for estimation of the overshooting using the satellite data is quite difficult, because you can't see it normally in the night. So usually in the night, this is where I would say this is the one that we use. That's the visible, the infrared image is what we use for overshooting. So much of this work in the concentric gravity wave side is usually, should I say, the OT is usually determined using the infrared image. So more information on this particular case, or let's say this literature, you can find it in et al. 2014. All right, so let's talk briefly about the governing equations, which I'll just mention. Gravity wave obey three basic equations. That is the equation of momentum, the equation of mass continuity, which is equation 2 here. Equation 1 is for the momentum. And then equation 3 is the energy. So these are the three basic equations gravity waves in general obey. And from these three equations, I'll say that one very important relation is being derived. That is the dispersion relation over here. And this dispersion relation helps us to relate the temporal component of the wave to the spatial component. So from here, we can estimate the period of the wave. We can estimate the phase speed, and as well as the wavelengths of the wave using this equation. This is just to mention actually, but I won't go much into this particular literature. Okay, so now let's come to Brazil. In Brazil, we are conducting let me say we are still conducting research on concentric gravity with using 3 all-sky imager observation sites. The first one is São João do Cariri, and then we have the second one, Cachoeira Paulista, located here. Then we have the third one, São Martinho da Serra. Okay, so having done, should I say this, one way for us to be able to see the concentric gravity wave is to process the images that the all-sky imager at these 3 locations would give us or would observe. But the imager gives us the images in a raw form, or let me see, original form, where we have the distortion of the lens, the fisheye lens, to make it look up or to appear this way. So it is important for us to process these images before we can know whether we have gravity wave in general or not. Sometimes playing the video alone using the, should I say, the original image, you could see, but this is just one image, so it's very difficult for us to really see what is going on. So at this particular point, this is the raw image. We have the stars, as we can see, the white dots. Then we have this particular strand of light here, which is the Milky Way. Then at the top and then the bottom, we have the influence of city lights or reflection from cloud. It can be any of them. So now, for us to continue and then have our gravity parameters extracted, we first of all need to remove the stars, because these stars influences the high frequency component of the wave. So in order to do that, we need to remove the stars. Then removal of the stars give us the second one, which is titled here, star removal, the B, where you could not see the stars any longer in this image. Then after that, we linearize it. Just to talk of linearization, we are talking about projecting it onto the horizontal plane. So by so doing, now we can see clearly. Now we have some concentric rings here, over here appearing at this particular point, clearly in this particular linearized form of the image. So in that case, as I said, it will be sometimes difficult for you to see it in the original image. So you just have to do it this way. And then this is the only form in which we can determine the wave parameters. So having done this or linearized this original image, now we can go ahead with the analysis of this dark and bright band we are seeing to determine our wave parameters. And to do that, for the concentric gravity, we selected 3 regions. And the 3 regions here is R1, R2, R3. The reason why we selected the 3 regions is to be sure if we have the same wave parameters propagating through these 3 regions, since we are, should I say, at that moment, only speculating that it's an overshooting, or it's only one point source that generated the wave. So we expect the wave in all directions to be the same. So this is just to test. But in a normal case where we have a linear gravity wave, you can select one region and off we go. But in this case, this is an adaptation that we came by in order to verify. After that, after we selected these 3 regions, the next thing we did was to now create this time series image, which in this case we selected only 10 images. So we arrange them in order of their time. Then from there we apply what we call the spectral analysis. The spectral analysis is basically governed by the Fourier transform. So that is just what we use here for each of them. So we take one region, then we apply the spectral analysis, we take the second region, we take the third region, then now we estimate our wave parameters. Since we have time constraint, I will kindly ask anybody who wants to know more about the spectral analysis can check Ras et al. 2004 or Nyassor et al., which is our current paper we just published on this case, 2001. You have more information over there. And now the next thing we did was to know the center of this circle, because mostly the center of these concentric rings agrees with the source location if the background wind is very low. So the first approximation we want to have or we want to use to know the source of this wave is to determine the center of the circle. So to do that, we pick the first concentric structures on the Oscar imager, which is this one. Then we apply this technique of using 3 circles on a bigger circle that we don't know the center. So to do that, we draw a small circle on the circumference of the circle without a known center, such that the 3 circles will intersect. So after we've gotten the intersection point of each adjacent 2 circles, those intersection points will also intersect at another point, which gives us the center of the circle. So in this case, that we observed on 24th March 2018, we apply this technique, and then this is the result we've gotten here. So we can see that the first determining concentric shape or rings that we use this approach to do, we could see that it perfectly overlaid the first dark band here. And then the red dot here is the center. And then we use the radius that we determined, actually using the Pythagoras theorem just here, because we have 3 points, this, and this. So you can take any of them and then you construct your right angle triangle. Then you get your radius determined here. So that is what we did. And this night, the radius was around 110 kilometers. So this is the application of this methodology here to determine the center. And as we can see in our previous, follow-up slide, you would see that the center here and then another method that we use, which is the retracing, will all point to almost the same source. Now, another methodology to talk briefly about is the retracing result. And I wouldn't talk much about it because I think Dr. Ego presented briefly on this, and it's quite in-depth. If we want to talk, we'll spend much time. So I only state the 2 most important equations that govern the retracing model. The first one is the equation of the, the brute velocity. Why? Because this equation is basically for the wave packet, the propagation of the wave using the energy. And then this second equation here, that is equation 6, is actually the wave refraction. Why? The basic theory is that this wave or wave generally propagates using the brute velocity to get to wherever they want to go. So in order to study the propagation of the wave, we use the brute velocity to actually trace it back to the source, that is back in time and space. And then since the wave is propagating in an atmosphere where we have wind as well, blowing across vertically, or we have the wind behavior also putting into account, then we should expect some refraction due to the wind. So we have to also come out with this particular relation, which actually is not my idea, but I think it's a theory based on Lighthill. So he came out with this theory. So by these 2 equations here, we are able to study the trajectory of the wave back to the source. And you can as well do it up into the atmosphere, depending on what you are looking for, if you want to know the source or you want to know where the wave propagated up to. And these 2 equations composes of all the important parameters you need. That is, you have the wind, you have the temperature, you have the density, the pressure, the wave parameters, everything in this. So if we really want to expand all this equation with all the separate components, it's going to be a lot of work. So just for a brief knowledge on this, I'll say this is a masterpiece for us to use. And now, for us to be able to know the next point of the wave, the next location, the next time, we use the Ranjikuta iteration method to solve these 2 equations in order to attain the next point back in space and time, or the next point forward in space and time. So that is the equation we use here to do it until when the energy of the wave is finished, then it stops. So that is where it's going to tell us that according to the model, this is where the wave either propagated to, or this is where the wave actually started from. So this is just a brief description on the retracing model. Okay, so some examples of concentric gravity waves that we have over Brazil. I'll start with these three cases, which we observe in São João do Cariri. In São João do Cariri, we have more than 25 cases from 19 years of data set that we have in São João do Cariri. One thing is, it's very difficult to observe because the very system that generated this wave normally tend to cover the field of view, as we could see in those animation that the clouds are covering the field of view of the imager. So that is one reason why it's very difficult to observe. And secondly, if you have a very strong wind, according to a model study, sometimes the wind tends to filter out the waves, so we can't observe them. So most of the time we observe concentric gravity when the wind is very low, or let me say it's very weak in the atmosphere. So out of that 19 years of data that we use so far, because we have more than 19 years, but we just use that one for the PhD work, the best cases have been selected based on some criteria. So I will not speak about the criteria, but I'll just show these images. For the first case that we have is on the night of March 11th, 2008. Then we have another selected case on September 9th, 2016, and then the third case on 25th May 2019, sorry. And then from that observations that we have here, we could see that this first and second case have kind of an arc-like shape here. But then the third case is elliptical. This is a different information that this configuration is giving us. And the information is that the wind is a little bit strong, which could actually influence the shape of the wave. So this is what the wind sometimes does. If the wind will not filter out the wave, it will distort the shape. That is the complete circular shape we'll be expecting. The wind will distort it and then sometimes make it look elliptical, just as we can see here. But the point is, we couldn't observe the complete elliptical case, so we could really see half of it or part of it. So after observing this wave, we want to investigate to see if this wave actually originated from the troposphere or was as a result of overshooting from the thunderstorm or the clouds. So we ran the ray tracing for these three cases. And then for the first case, let me give a brief description on the legends here. One, we have the model wind, which we use the mirror 2 and then the horizontal wind model. So the model wind shows that we are running the ray tracing considering the wind. And then the zero wind here means that we are running the ray tracing without the wind. The reason is that we want to see the effect of the wind on the propagation of the wave. So when we run it in these two modes, we'll be able to see the ideal situation and then the real situation. So that is the reason for using the model wind and then the zero wind. Then we have our observation site determined by the black triangle. Then the blue and then the red dots here shows when the wave stop for both, that is the model wind and then the zero wind. Then the black dot here actually shows the reflection, the first point of reflection of the wave, which of course we do not have in this case, so you couldn't see it in the images here. Then the plus sign here shows the crest of the wave, where we started, the first crest where we started the ray tracing from. Then the determined center of the concentric ring or arc is determined by or depicted by the black diamond here. Then the asterisk sign here shows the tropopause position. So from these two plots, the upper panel shows the propagation of the wave trajectory with altitude and time. Then the lower one shows the propagation of the wave in space, that is longitude and then latitude. So as we can see for the first case, we could see that both the ray paths for zero wind and then the wind model using it in the ray tracing are all pointing to almost the same position here. So the center is also within the same area for this particular case. And then we have a convective system here, which is having a very cold, bright cloud top temperature. So indicating that this wave this particular wave is possibly generated by this system here or any system located around. But looking at the region here, this is the only system that could have the higher probability of overshooting to generate this wave. And then to mention this particular red dot circles we can see here is actually the first concentric structures we saw on the image. So after we determined the radius and the center, we constructed it here to show the ideal situation or the ideal case of the concentric wave if the imager happens to observe it completely. Now, coming to the second case, we could see that that is the case of September 9th, 2016. We don't have any convective system here. And this is our center. And then the ray tracing is also ending somewhere here, which is about 300 kilometers away from the center. So this result is giving us a different conclusion. So we cannot say this concentric gravity wave is generated by any convective system, which we have other mechanisms that have currently been introduced. That is the secondary gravity wave, which is a wave that is generated as a result of a wave that is generated primarily by a convective system or a wave generated in the troposphere that dissipates and then generate a second wave. So that secondary gravity wave usually also have concentric nature. So this is giving us an idea that it's possibly a secondary gravity, which I'll talk briefly about because we are now doing investigation on this particular case. So I'll leave it here, and then in the follow-up slide, I'll talk about that. Then the last case that we have selected here is the elliptical case, as we can see over here. Now, this case is also giving a different information because one, the ray tracing has ended somewhere here, and then we have our convective system somewhere here, which is not far from the ray tracing tropopause position anyway. But then the center of this ellipse is far away from the cloud top or this system that we are, the ray tracing is identified as the possible source. So this is also giving us an information that the wind during this event is quite strong, even though it could not filter it out completely, but could dislocate the position of the wave as it propagates from the top of the cloud to the OH emission layer. So this is also another case that I'll talk about in the follow-up slide. Okay, now, it is important to know if the wind was strong or not, because for us to observe concentric wave, it means that the background wind was weak to permit it to have that concentric nature. If not, it would have been filtered out or possibly distorted. So we observing the concentric gravity wave is a first indication that the wind is low. So we decided to do a blocking diagram. This blocking diagram is just based on the concept of the fact that where you have the regions where you have the wind, it is not possible for gravity wave to propagate through unless the gravity wave phase speed is very strong, or let me say stronger than the wind. That is where it might survive the blocking diagram because the blocking region, because within the blocking region, you can have the critical level, which will filter out the wave and then refract the wave and cause any other issues to the wave or absorb it as well. So for us, observing the concentric gravity and still having this region here, it means that this wave is having a very high speed, as we can see here, that the phase speed is far, far higher than the wind during this event. So the wave could actually survive this region and propagate to the observation emission altitude as we have observed. Then we set this standard here, that is 30 meters per second, because a model studies by Vadas 2009, Thor 2009, as I cited earlier, showed that when you have the background with less than 30 meters per second, you have a higher chance of observing the concentric gravity waves. So we set it here so that we could see which region within which we could have the blocking region, and then compare it to see if it is possible for us to not to observe or to observe the wave. It's just to test the theory again to see if this is exactly what is happening in our case. And we've observed that that is exactly because we could see that the wave is propagating eastward, and then the wind was actually towards the westward, but the magnitude of the wind is lesser than the phase speed of the wave. So this wave could survive, explaining why we were able to observe the concentric rings in the OH emission layer. Now, coming to the last case, because I'm picking the first and then the third, the second case will be another discussion. So coming to the last case here, I would say that we have the wind to be very low compared to the phase speed. So we have the 30 meters per second mark here, and the wind is very low or within the 30 meters per second, less than that. So we expect to have almost a complete circle if this is what the model wind is telling us. But then having an elliptical shape tells us that the wind was quite stronger than this model wind, the model wind representation here. So we have to go further to do further investigation to see why we could see that elliptical shape. And then let me say, on our side, we were favored to have meteoroidal wind at São João do Cariri that night. So we will use that one to briefly justify the reason why, one, we have the dislocation, or let me say difference between the position of the center and then the source position determined by the retracing, and then why we have elliptical shape. So now to explain the dislocation in terms of the center of the wave and then the position of the source position determined by the retracing, I would say that we use the vector diagram here between 22 UT and then, 20 UT and then 22 UT, because the wave was observed within this time range. So we realized that somewhere around 82 kilometers, the wind was towards the southeastern direction. But by 85 kilometers, the wind started changing to northeastern direction. And then around 88 kilometers, we have it towards, let me say northward. Then by 92 kilometers, it is now towards the northwestern direction. So we could see that the wind changed its position from southeast to northwest, okay, just within about 10 kilometers. And all this region happens to fall within the OH emission layer. So this is giving us an idea about why we have the center of our wave here to be shifted towards the northwestern direction of the source. And then now the center is also towards the southeastern direction of the source here is also showing that the center is towards the southeastern direction. Okay, so this is one explanation we can give, because the wind actually changed the position and is in agreement with the source position determined by the retracing and then the center that we have determined. Now, the next thing is that we have what we call a hodograph. The hodograph just gives an idea about the position or the direction of the wind at a specific altitude, which in this altitude we have 88 kilometers and then 85 kilometers. So at 88 kilometers, between 1930 and then 2030, we have the wind to be towards the northeastern direction. Then at 830 to 2030 to 2130, it has changed its direction again. So it's now towards the southwestern direction. So this kind of change in position could possibly be used to explain the compression of the concentric ring. If we have a complete circle, this wind here could possibly compress that side of the circle. And then getting to this point and then changing its direction could also compress the other side, thereby causing that particular regions where the wind is trying to compress to look more closer, or the radius to reduce, making it look elliptical in shape. And then looking at the same, let me say, doing the same analysis, that's the hodograph, we realized that at 85 kilometers, we have the same behavior of the wind, which is towards the northeastern part. And then at 2030 to 2130, it has changed its position to the south western part. So as a result of that, this could also justify that within this OH emission layer, it's not only that the vertical propagation of the wave is changing from southeastern to northeastern with height, but at the same time is kind of compressing the part of the concentric ring, making it look elliptical in the OH emission layer. Actually, that is the observed thing, so that is what we are seeing. So using these two descriptions, we are able to justify why we have this configuration and also the shifting of the source position from the center of the wave. This indicates that the wind actually was quite strong during this night, but the model wind could not really explain that for us. Okay, coming back to the middle case, that is a September 9th, 2016 case, where I said we don't have any convective system nearby. This is just another diagram showing the concentric cycle here, which is just traced from the arc that we found. And then this is where São João do Cariri is located, and we have, actually the field of view should be located within this region where we observe the wave. And looking at this location, and then the nearby convective system that we have here is about 1,320 kilometers from the observation site. And also the wave parameters we have this night is too small for such a wave to propagate 1,320 kilometers away to the field of view. It will be, should I say, filtered out or dissipate quite early. So looking at that configuration or this configuration, we have to go further to investigate if the concept of the secondary gravity wave I spoke about earlier is the possible cause, or let me say the possible reason why we observe the concentric wave, or it is something else. But then further analysis showed that during this wave event, close to the observation site, that is this place, and then close to the convective system, we have the Seba temperature profile or sounding. So from the sounding, we have this temperature profile, and then we saw an inversion region here because we are expecting that the temperature will also be decreasing, and then will be lowest within the mesopause region. But we have an inversion here showing that this inversion could theoretically could possibly cause wave ducting, and then as a result of that, it can trap the wave and then cause it to propagate a longer distance, which is also something we are just speculating at the moment, but we will do further studies, and if I have the opportunity to maybe give another seminar in the future, we could specifically explore this particular case, and we will share with you our findings on this case. So for the cases in Campina Grande, I'll say this is all that I have to show for now. And then we go to the next one, which is São Martinho da Serra, down south, southern part of Brazil, where we have, I would say, the best and then convincing cases mostly. And during that period, we have only 3 years of observational data, as at the time I was doing the analysis. That's 2017, 2018, and then 2019. And then we chose these 3 cases, which at the moment has already been published. So details on this, you can kindly find it here to just have a look at what we did over there. Now, for the case of October 1st, 2017, which I showed in the animation first, this is how it actually looks. And then coming to the 24th March 2018, where we have almost a complete circle. This is where we have the best case ever over Brazil. And then 18th October 2018, we have another case also observed in São Martinho da Serra. And as we already know, as I stated, observing concentric gravity means there have been some overshooting, and maybe this is due to clouds. And we could see the cloud also over the image, so we are not far from finding our source. So what we did was to apply the ray tracing as well as to determine the center of these waves. And this is the result we had. For this particular case, that is the October 1st, 2017 case, we could see that the zero wind in terms of the horizontal propagation could not go far, but the model wind could go very far. And its tropopause position is actually closer to the regions where we have the coldest cloud top temperatures, which is within this region. So this ray tracing actually is giving us a very important information here. And then we could as well see our center here, which is not that far from the tropopause position determined by the ray tracing. So this and this are actually pointing, but the zero wind could not give us any information apart from telling us that the wind was quite varying and quite strong during this particular night. And then we could see that the time the wave was generated, indicated by the zero wind, is about 2.5 hours later than the one that the ray tracing with the model wind indicated. So from this result, one can say that the wind was strong and then varying on, not strong per se, but was varying and strong enough to actually displace the wind or to also influence the propagation of the wave. Second case, which is the 24th March 2018, as I said, is so far the best case we have. We could see that we have the center, then we have the tropopause position determined by the ray tracing as well as the ray tracing, both wind and zero wind, all within the same region. And this is the case where we have almost a complete circle. So this ray tracing is just telling us that the wind was extremely low this night, and we could see it also over here, that there's no much difference between the zero wind part and then the model wind part. So they are all pointing to almost the same time the wave have been observed. Then the third case, also having a similar behavior like the first one. The wind was quite varying, but it was rather unfortunate. Later we realized that the wind was not more realistic enough to help us to locate, but it's actually just giving us an idea about where this wave is coming from, because we have the tropopause position within this region, whilst we have the center here, and the center is corresponding to the region where we have the coldest cloud top temperature, which signifies overshooting or the source position. So this wind could give us an idea, but not a complete information about this particular event. But we further did some background studies on the tropospheric activities, and then we found out that this wave was actually generated by this particular overshooting or the convective system here, which I think will also be another subject to talk about, because it's a quite a complicated analysis, which we will have to talk specifically on. So the next thing we did over here is to now see if our wind during this night is low or it is not low. Now, from the first case, that is October 1st, 2017, we realized that the blocking diagram over here was mostly, let me say, northward. And then our wave is also propagating towards the northeastern direction. So part of the wave was found within the blocking region. And this has affected the wave to propagate horizontally. As we can see from here, you could see that the model wind actually propagates horizontally for a long time, which is about, should I say, 3 hours to the time of observation of the wave. So this is quite an interesting result, showing that the wind could influence the longer horizontal propagation here. The only good thing was that the phase speed of the wave was higher, so it could survive this region. But it does still have some effect on the propagation of the wave. So we have this agreement between the ray tracing, the wind, and then the observation that we had. Now, for the second case where we have a complete circle, we could see clearly that our 30 meters per second mark here, the wind is within this mark. So the wind wasn't more than 30 meters per second, which is an indication that during this particular event, the wind was weak, and then the phase speed of the wave was very strong, so it couldn't really have effect on the concentric structures that much. And this is one of a kind of a result that we have so far. And we could as well see this in the Oscar image that I showed earlier on. Okay, for the next case, that is the last case for São Martinho that I'm presenting on. The wind and then the propagation direction of the wave are quite a little bit opposite to each other. So in this case, I would say that even though we should expect some influence, we couldn't really influence this that much, because first we observe the wave in the OH emission layer, but the wind is also depicting quite a slight different configuration here. Even though it permitted the propagation, as I said earlier on, the wind was not so realistic, or it didn't help us to really determine the source. It only pointed to the region, but not as the other cases. But for this, we could only use the configuration of the source parameters to really justify what we are seeing, and also to justify the retracing results. Since we are not using a more realistic wind profile, we are just using a model wind profile. So that is the only way we could justify our result. So with these three cases from São João do Cariri and then São Martinho da Serra, so far those are the cases I touched in the PhD work. And from Cachoeira Paulista, I have not really worked on that, because they also presented a different configuration altogether. So we left that particular one for future work. So in summary and then in conclusion, I will say that for São João do Cariri, we have 3 cases presented today or discussed today. And then from this, we have 2 of them being arc-like, and then 1 semi-elliptical kind of configuration of the wave front. Then the backward retracing for 11th March 2008 and 25th May 2019 located or identified deep convection as the possible source of this wave, whereas the other case, which is the 9th September 2016, do not have one. So observing an elliptical wavefront, we use the the meteoroidal wind to explain further why we have the dislocation between the source position and also the source position determined by the retracing, and then the determined center of the ellipse. We use that one to explain possibly what happened for us to observe that. Then for the case of the September 9th, we are actually speculating, or let's say suggesting, that it could possibly be a secondary concentric gravity waves, because one, the ray tracing didn't identify any nearby convective system, and then the convective system that we do have is 1,320 kilometers away. So it is not possible for a wave of such parameters to propagate that much, even though we have our SEBA profile showing some dark region, but temperature inversion region, but we needed to investigate further into that for us to finally conclude on that case. Then from São Martinho da Serra, we presented 3 cases here. 2 of them are arc-like, and then 1 is almost having 360 degrees complete circular wavefront. And then ray tracing for this case is actually show that it's a convective system that overshot to generate the waves. And then a blocking diagram also in all the 3 cases for São Martinho da Serra showed that the wave could survive the wind whilst it's propagating, because 1, the phase speed of the wave is stronger. It's very strong. Let me say, having a high phase speed, far stronger than that of the wind. So they could survive the wind and then propagate to the OH emission layer where we observe them. So for the cases of São Martinho da Serra, anyone who really wants to know much of that, because of time, I couldn't talk in details on those things. Please, you can kindly get this information over here. Then you download and have a look at what's happened. And I'll use this opportunity to thank INPE for the opportunity for my doctorate program, and UFCG for the master's program, and then CMPQ and CAPIS for the financial support. And then I'll thank this organization for the data that is embraced, which provided the Oscar images. Then we have CPTech that provided the cloud top, infrared cloud top images. Then these images provided by CPTech is actually provided by GOES, so I give them thanks. And also the wind, that is the mirror wind, is also gotten from this NASA website, NASA Earth Observation Data and Information System. So thank you all for your presence, and then the opportunity once again to share with you briefly what I've been doing so far since I left UFCG. Thank you very much.
Thank you so much, Prosper. So now I will open for some questions. Então, vocês podem fazer perguntas, podem colocar perguntas no chat, abrir o microfone. Se desejarem fazer perguntas em português também, acredito que o Prosper compreende. Prosper, you understand Portuguese, right?
Yes, but in case I don't understand clearly, I'll ask for you to please translate for me.
Okay, I can do it for you. Então, quem desejar fazer perguntas, por favor, fiquem à vontade.
Marcelo, só abrindo a discussão assim para o público, né, que como assim, nós não temos muito especialista na audiência, né, vocês podem fazer perguntas, inclusive com curiosidades relacionadas ao trabalho, que não seja nada tão técnico, tá? A gente, assim, as mais diversas perguntas sobre o assunto, a gente pode tentar responder e esclarecer, né? Eu queria só que vocês percebessem, né, que Próspero ele está apresentando aí alguns resultados, que são resultados importantes. Um desses trabalhos, que foi de São Martinho da Serra, lá na região sul do Brasil, já foi publicado numa revista de relevância internacional, no JGR, e a gente está com um artigo em revisão e o outro em preparação, que logo, logo a gente vai submeter também. Então, a gente tem dessas pesquisas envolvendo ondas de gravidades concêntricas, a gente está com 3 artigos aí, no final da tese de Próspero, o que eu acho, assim, bastante expressivo, né, para o trabalho que ele desenvolveu, tá? Então, assim, tentando, de uma forma geral, simplificar o que nós estamos fazendo, nós estamos, a partir de observações da aeroluminescência, que é semelhante a um equipamento que nós temos aqui em São João do Cariri, nós observamos ondas de gravidade de formas circulares, e essas ondas de gravidade nós estamos estudando, investigando quais seriam as possíveis fontes dessas ondas de gravidade. Tá? E para isso a gente usa alguns modelos matemáticos e combina com observações para tentar dar um diagnóstico sobre as condições de propagação das ondas dentro da atmosfera. Então, vocês podem fazer as perguntas que assim desejarem, tá? Podem ser perguntas bem básicas, até o que é onda de gravidade, e a gente pode tentar responder, tá? Então, fiquem à vontade. Prosper, there is a question on chat. I guess you can read and answer, please.
Okay.
Luciano is asking, what is the origin of these waves? What produces these waves?
Okay, then let me go to the first slide, then we can look at it from there. Okay, so from this figure, all the cases that I presented today on behalf of myself and then all the collaborators, these waves originated from the troposphere. And the mechanism through which they originate is the overshooting. The overshooting is more or less like pushing of the tropopause into the stratosphere. Okay, so within the cloud, we have this updraft acting like a vertical oscillator that is just moving up and down, and then is hitting at the tropopause at a particular frequency, thereby generating this wave. So the waves basically from here is generated by the convective system, or let me say clouds, in the lower atmosphere, that is the troposphere.
Próximo. Wind shear.
Yes, please.
Wind shear of the horizontal wind, vertical wind shear of the horizontal wind. With this kind of situation in the atmosphere, can we generate these concentric gravity waves? Suppose that you have a jet stream in the stratosphere. Is the jet stream able to create concentric gravity waves?
Sincerely speaking, I have not really looked at that, but the jet stream, in my point of view, it can influence the wavefront. If already we have an existing wave, it can influence the wavefront, but to generate the wave itself, to me, it's possible, it could, because I know in literature we do have jet stream generating gravity waves, but for concentric gravity wave, I've not really come across literature so far that spoke about that. So I can't categorically say that jet stream can generate the concentric waves. But then, considering the secondary gravity wave theory, I would say possibly it's possible, but I cannot categorically say it can, but it's possible that would be.
Yes, it will be my second question, because if you are trying to investigate this concentric gravity wave generated by second gravity wave, when you have the second gravity waves, in fact, we have the broken of a single wave in a portion of the atmosphere, causing acceleration of the background atmosphere, and with this deposition of the momentum and energy, we can generate a secondary spectrum of the gravity waves that can be concentric or not. If you take it in mind, we can expect that a strong wind shear can generating concentric gravity wave as well. Well, that's my opinion on this point.
Okay.
Então, mais alguém tem alguma pergunta? Não? So, all right. So let's finish here. All right. Okay. Prosper, thank you so much for the great seminar and the discussion. Gostaria de agradecer a todos pela presença e a participação, e gostaria de pedir para que vocês, para quem puder abrir o microfone, para que a gente possa agradecer ao palestrante com aplausos, por favor. Thank you so much, Prosper.
Thank you all so much for the opportunity as well.
You're welcome. Bye.
Bye.
Então, esse foi o último seminário de semestre. Vocês vão receber e-mails sobre os próximos, quando retornar. Tá bom? Muito obrigado a todos.